So yesterday we spent some time talking about proving algebra statements and using deductive reasoning and two-column proof for showing that algebra equations were able to be solved and justifying why we were able to solve equations. Today we're going to start looking at that more in a geometric concept and talking about geometric proof. I'm going to spend quite a bit of time talking about proof over the next few days, but before you get yourself all worked up about it, it's not the biggest part of our test in this chapter. There is going to be a proof on our chapter test, but only one when it comes to things that are not just algebra, when it comes to things that are more geometric. It's not going to be too terribly tough, but it's also not going to make or break your entire grade based on this one proof. So let's work as hard as we can on the proofs. They are a little bit difficult to understand sometimes. They do take a little time. Some people get them right away, and that's fantastic. For some people, it really takes a lot of repetition seeing this done before the light bulb starts to go on. That's okay. We'll do the best that we can. We'll keep working on it. I'll keep demonstrating them. We'll keep working on them in class. And hopefully that light bulb will go on pretty quickly for you. Nonetheless, we are pressing forward, and here we go. And yes, those notifications are still popping up. I don't know why. I've set them to not pop up anymore and set the preferences. Nonetheless, they seem to want to do that. So my apologies. Properties of segment congruence and properties of angle congruence. We talked about this yesterday. Basically, the transitive, reflexive, and symmetric properties apply to both segments and angles when it comes to congruence. We showed that it applied to their measurements yesterday. Today we're saying they also apply to congruence. So I don't have to, it saves me a few steps this way to say it applies to congruence. It's not a big deal. Name the property the statement illustrates. We did this in class yesterday. Actually, we did it in class today. If you're watching this tonight, the same night as we did the lesson. So if angle T is congruent to angle V and V is congruent to R, then T is congruent to R. Again, we see the structure if and then. That generally indicates transitive property. Now, some are going to get excited about this and say you need to say transitive property of angle congruence. To me, that's a bit excessive. If you can identify it as being transitive, that's good enough for me. I'm happy. If JL is congruent to YZ, then YZ is congruent to JL. What did we do? It's not exactly the same. We flipped the order, flipping the order. It was exactly the same. That'd be reflexive. But again, it's this if-then format that flips the order, tells me it's symmetric. One of the things that can kind of help you out here if you're kind of looking for a shortcut, if we see if blank and blank, then blank, that's usually transitive. That's the format for transitive. If I see if blank, then blank, and it's the same thing, just flipped, that's symmetric. And if I just see that something is congruent to or equal to itself, that's reflexive. Reflexive usually doesn't show up in a conditional statement. Symmetric almost always does. And transitive always shows up in that if and then, almost always in that format. So can help you kind of sort things out. All right, the concept summary of a two-column proof. A two-column proof in geometry basically works the same way that it worked with algebra. We have two columns. We have our statements on the left. We have our reasons on the right. We start with some given information. That gets plugged right in, and the reason is given. Now, in a geometric, unlike an algebra two-column proof where you just have to solve for X or solve for P or solve for whatever you're looking for, usually in a geometric proof, they're going to tell you what it is you're trying to get to, tell you what that final destination is, tell you what the final answer is. In this case, they said, prove that angle 2 is congruent to angle 1. That's our destination. That's where we wind up. We got to figure out all the steps it's going to take to get there. Again, I go with the whole driving analogy here, is if you're going to drive from your house to Woodman's, this is your house. You're starting at home. You know where you're going to start. You know where you want to wind up. But you need to know all the directions to get there. You know all the step-by-step directions. Where to turn, when to turn, what direction to turn, that sort of thing. And that's what's going on here, are the step-by-step directions on how to get there. So we write down our steps on the left, statements based upon what you know or conclusions, things you're given maybe. Our reasons, notice what we're using as reasons in our proof. Our reasons can be definitions, postulates, already proven theorems, properties of algebra, anything like that. Anything that is given factual information, because this is deductive reasoning. We have to have a reason why. Now, right now that seems, well, how do I know which one to use when? How do I know what conclusion to make? This isn't like algebra where you can just, okay, I know if I see this, I have to subtract from both sides. I know if I see this, I have to divide both sides. It doesn't work like that. This is very much a puzzle-solving process, which makes it a lot more difficult for some people. For some people, this is great. You love puzzles. And puzzle solving is something you do really well at. Others of you are going to struggle with this, and that's a fact. You're good, but it's a process that's good to learn. Because, again, real-world situation-wise, is anyone going to ever ask you to come and say, write a two-column proof to show me that the angles are congruent? Of course not. It's never going to happen in the real world. But are you going to be asked to justify why you want to do something? If you're going to work someplace and, say, have a budget and need to be able to justify why you need to have $30,000 for this new piece of equipment, you better be pretty good at making a logical argument. And that's what this is. These are step-by-step logical arguments as to why something needs to be done. So this process that we're learning of making a logical argument, that's really what we're working on here. Geometry is simply the vehicle we're using to help teach you the concept of making logical arguments. And that's really what we're doing here, is teaching you how to make logical arguments. Because that's a skill that's going to be valued by employers and just valuable in life in general. So geometry, we use geometry as a structure to help teach that concept, but really that's the concept that we're going for. So as we're working through this, yes, the geometry is important. Yes, the geometry is what we're testing you on, but the big picture skill we're working on here is using logic and being able to make a logical argument. Let's take a look at how it's actually done a couple times. Here we go. 6 steps are given of a 2-column proof. This is a fill-in-the-blank proof. And it's a pretty great way to get started. It says, copy and complete the proof. Here they want you to find the value of x. Given t is the midpoint of SU, find the value of x. So what are we given? We start with our given. T is the midpoint of SU. What did we write down for our first thing? T is the midpoint of SU. Our reason for that is, well, it is given. Now, here's where it gets interesting. We have to ask ourselves, what does that mean? There's a vocabulary word being used here. The vocabulary word we're seeing in this statement is midpoint. What does it mean that T is the midpoint of SU? Usually when we see a vocabulary term in a given like that, we're going to use the definition of that term to draw some conclusion. And for T to be the midpoint of SU means that segment ST is congruent to segment SU. That's what this means. So if our given uses a vocabulary term like midpoint or bisector or complementary or supplementary or something like that, we generally use a definition of that to draw some sort of conclusion or set up some sort of equation or relationship between pieces. And so that's our reason why. from there, well, what does it mean that ST is congruent to TU? Can I make any conclusion on that? If two segments are congruent, it means their measures are equal. Okay, great. So I'm going to go from congruence to equal measure. Whenever I do that, that's a definition of congruent. Whenever I go from saying two things are congruent to saying they have equal measure, or backwards, saying they have equal measure to saying they're congruent, that's using the definition of congruence. You're going to see that a lot in proofs. Next thing we did is said, okay, ST equals TU, the measure of ST equals the measure of TU, but what do we know? ST here is 7x. And TU is 3x plus 20. So what do? We change the ST into a 7x because they have the same value. We change TU into 3x plus 20 because they have the same value. That is an example of substitution property. So two things that are, so I take that measurement and I rewrite it in terms of x because I know what it is in terms of x, but I'm not really changing anything. I'm just rewriting it a different way because I know they're equal values. That's substitution. Next, we do our algebra steps because we now are in algebra mode. 7x equals 3x plus 20. I'm going to subtract the 3x from each side. So 4x equals 20. And then we already had subtraction property. And from here, what am I going to do to both sides? Of course, we're going to divide. So that's division property. Now notice again, they wrote subtraction property of equality. I'm fine with division prop. We can shortcut things a little bit and save ourselves a little bit of time with some minor shortcuts. We don't want to go too far because it can get confusing. But that's an example of a full-on 6-step proof to find the length value of x. Let's look at a couple more. Given M is the midpoint of segment AB, prove that AB equals 2AM, or AM equals 1/2 AB. Okay? So we want to prove both things. So here we're going to go. Here we go. First step. First step should always be easy because it's whatever we're given. M is the midpoint of AB. And that's given. Now, we have a little advantage on the smartboard because I don't have to redraw the picture onto my paper. And if you're working out of your student journal, yeah, you can just work with that in your paper. But if we're working out of the book and there's a picture associated, I always want to see that picture redrawn with the proof. You always want to have the picture with you. And mark the picture. What does it mean? If M is the midpoint of segment AB, that means what? What is it telling us? Well, if M is the midpoint of a segment, it means that segment AM is congruent to segment MB. And what tells us that? Vocabulary word. So definition of midpoint. What does it mean to be a midpoint? What is the definition of midpoint? It tells us that segments are congruent. If they are congruent, it means they have the same measure. So AM equals MB. So that's a definition of congruent. Now, here's where things get interesting. AM equals MB is great, but I want to prove that AB equals 2AM. Okay? This is going to be a little bit tricky. but I'm going to walk you through it. Again, this is probably a little bit above what you're going to be expected to do, but I want you to see it done. What I want to do is I want to say, okay, what if I added another, I want to get a 2 a.m. Well, I can get a 2 a.m., not the time of day, by saying that a.m. plus a.m. equals a.m. plus mb. So what I do, I'm adding an a.m. to both sides of the equation, aren't I? That's addition property of equality. I'm allowed to add the same thing to both sides. But a.m. plus a.m., it's the same thing. That's 2 a.m. So that's a substitution step. Sorry. Now here's something we're going to see quite a bit. This side, AM plus AM is 2 AM. That's easy, but I have AM plus MB. What does AM plus MB equal? AM plus MB. Oh, this is where we get a little tricky. AM plus MB equals AB. Segment addition. Property. Or postulate. Segment addition postulate, I think it is. We'll just call it segment addition for now. That gets the idea across. You're saying, well, wait a minute, what happened to 2 a.m.? You're right. I'm kind of taking a break right here and stating something I need to know so I can do a substitution. That's tricky, but it's something we're going to do a lot of. It doesn't always just work in order. Sometimes you have to throw something in a little bit on the side. And if AM plus MB equals AB, then I can change. I can take this AM plus MB and this AM plus MB. So they're the same, so I can plug this in its place. 2 AM equals AB, and that's a substitution. Now, if that's all I needed to prove, I'd be done. AB equals 2 AM. They're saying, wait a minute, it's out of order. You're right. It is. We could flip it and use symmetric property. I'm not going to be picky about that. We also have to show AM equals 1/2 AB, so if I divide, or multiply 1 by 1/2, it's division property. It's a tricky proof, folks, but that's what a proof looks like. It's 8 steps. That's pretty long. But again, this is really demonstration mode. Remember, you're going to be working on these in class with help. We may be going over more together in class. I would not be at all surprised if I'm going to spend some time in class actually doing things in more large group settings tomorrow. That's as far as I'm going to take us for today. There is one more proof in the notes, but I think these notes have taken long enough. Please be reading the section of the book with us. Please be looking at the examples in the book. We'll be looking at things a lot more in class. This is a tricky part, but it's important that we get into it. See you in class.